Hello. Greetings, everybody. We'll start in a minute or so. I am Professor Ryan Shiftia, chair of this session. So it is my honor to present our speaker for today, who is Dr. Santanu Ghosh from IIT, India, who will talk about embedded metal nanoparticles, shape engineering, electronic and magnetic properties, and experimental and theoretical investigation. So before the speaker starts, I would kind of draw his attention to check kind of the share, so the share function and so the sound and the video. And I have also to say that I have been asked by the organizer to be very strict with the time limit of 15 minutes. Therefore, please do program to finish everything in 15 minutes. So therefore, let's give now, so let's give a round of applause to our speaker. So Dr. Ghosh, I see you there. Is everything fine?
Yeah, hello, Professor. Yeah, so shall I share slide?
Yes,
I
you may
also
start.
have a recorded talk, but I can share slide also.
Since you are live, you can share it. And
yeah, sure. Is it visible?
Yes, it is. If you can make it full screen.
Right? Yeah, I made it. Is it all right now?
Yes.
Shall I start? Thank you, Chairperson. I am thankful to the organizers for giving me an opportunity to speak in the third AAA-FM UCLA International Conference. The title of my talk is Embedded Metal Nanoparticles, Shape Engineering, Electronic and Magnetic Properties, and Experimental and Theoretical Investigation. I belong to Department of Physics, IIT Delhi, and this is our institute. It's a beautiful campus now. And it's an institute of eminence in India, which was declared by the government of India in 2018. And this is a nanoscale research facility which we use all departments and centers across the institute for the research work. The outline of my talk is nanoparticles embedded in silica matrix and their shape engineering, and then engineered nanoparticles for tuning electron emission and magnetic properties, and finally I'll summarize the result. Now the first part is nanoparticles embedded in thin silica matrix. So we grow nanoparticles in embedded nanoparticles in silica matrix by a process called atom beam sputtering technique, where an atom source is used, and this actually sputters silica as well as the metal which are glued to the silica target. And eventually, after sputtering, they fall on the substrate, which rests on a substrate holder, which also rotates, so it forms a uniform film. And in this particular study, I will discuss about two films. One is nickel SiO2 granular films, and another is iron cobalt SiO2 granular films. And these are the deposition conditions which we use during the deposition process. So after we grow the film, we do Rutherford backscattering spectrometry, and in this we get to see the different element present in the sample. And here you can clearly see the presence of nickel, silicon, and oxygen. By fitting the spectra, we determine the thickness. And we have grown these samples in 3 different temperatures, annealed the sample rather, at 200, 400, and 600 degrees centigrade in order to grow the particle size as evident in transmission electron micrographs. And the particles which we grow in a high resolution microscope, we can see they are more or less nearly spherical nanoparticle. And with this spherical nanoparticle, if we bombard with ion, one can change the shape of this nanoparticle. And the idea is that suppose we pick up one nanoparticle and bombard it with ions with million electron volt energy range. And according to this particular theoretical formalism, that after the bombardment, there is an electronic temperature spike in the electronic subsystem, which eventually gets coupled to the phononic subsystem by electron-phonon coupling. And because of temperature spike in a very short time scale, we can observe what is called a thermal spike in the metal nanoparticle, as well as a thermal spike is seen in the surrounding silica matrix also. And if the spike temperature is higher than the melting point of the materials, then they melt, and eventually when they come back to the equilibrium condition, we expect that there will be a change in the particle shape. And the same thing which we observe in transmission electron microscope, you can notice that in transmission electron microscope, after irradiation, the particles which we observe, they are all elongated. So we call them shape engineered nanoparticles. One can engineer the shape by changing the irradiation fluence, therefore the shape engineered particles. Now, and more electronic structure point of view, if we look at the EXAFS results also show that the EXAFS peak intensity decreases drastically after the irradiation, which indicates that there is a lot of defects in the system. And also from DFT calculation, it has been shown that the particles shape changes. So once we have these shape engineered or shape modified particles, we do two studies. One is tuning field emission and the magnetic properties. So electron emission is a process which is known for many years, and we know that the electron emission is a high temperature process. It is thermionic emission. The theory was given by Professor Richardson in 1928, which is also known as thermionic emission by Richardson. And we all know these electron sources are extremely important. All these equipments what I have shown are the laboratory equipments where we use the thermionic source. But one can change this particular concept. One can have an electron source by a process called field emission, where one can have engineered materials on cathode, and applying little bit of bias, one can get the electrons out from this, and a completely cold process by quantum mechanical tunneling, that is called field emission. And one can make a display using this field emission source. One can make X-ray generator using this field emission electron source. And one most popular application of this field emission process is the electron microscope. We all know that electron microscope, people use this field emission electron source. And again, the theory was given long back by Professor Fowler and Professor Northam based on quantum mechanical tunneling process. But there are certain challenges of material scientists, that what is required is the aspect ratio should be high, there should be high current density, and turn-on field should be low. So several materials we have investigated out of this embedded metal nanoparticle system, which I am going to talk here. And this is a typical mathematical equation which is given by Fowler and Northam, and field emission process depends on a quantity phi, which is work function, and the field enhancement factor beta. Now with this embedded metal nanoparticle, when we did a field emission measurement, we could observe field emission current. However, the field emission current density is quite low, and definitely is not something which one can use as a field emission electron source. After that, we have used those shape engineered metal nanoparticle. Now you can observe that this is a green line which shows the current density of the particle which are spherical, not shape engineered, and this is a current density which is almost 500 times higher for the particles which are elongated shape. So there is a huge enhancement in the current density, and this can be tuned by changing the fluence. So one can do what we did actually, the out of plane resistant IV measurement. In that also, in out of plane IV measurement, what we have seen, it's the current density is much higher as compared to in plane current density. So this clearly tells it whenever there is an elongation of the particle, there is an easy path of electron flow. So now again we went back to the thermal spike calculation, which I have already discussed, and for different particle size we have done the simulation, and one can notice the temperature of the lattice is almost 4000 to 6000 Kelvin range. So it's a very high temperature, which eventually leads to a very high an elongation of the particle, of course, and a very high enhancement of the current density. So this is one aspect. Another is in ultraviolet photoelectron spectroscopy, what we have observed that there is an enhancement of density of state of electron also near Fermi level, which actually makes this electron tunneling much easier, eventually leading to the higher current density. So it is basically combination of two effects. One is elongation of the particle, making easy path of electron emission. Another is enhancement of the density of state near Fermi level, and combining these two gives very high current density of the shape engineered particle. And we have used this shape engineered particle in various devices. We have already demonstrated a prototype field emission microscope, where we have used that small source, and which is just integrated in a very small module, and one can put it in electron microscope sources to show that, and the source is simply this embedded metal nanoparticle. We have also developed a field emission entire field emission setup in our laboratory, which is much cheaper as compared to what people do with the commercial setup. And now we are making an X-ray source based on this field emission electron, and the testing is under progress. Now the second part is the tuning of magnetic properties. So we all know that there is a big discovery, which is giant magnetic resistance, and Professor Elmod and Professor Peter Guenberg, who discovered this giant magnetic resistance, where one can see very high resistance at zero field, which eventually falls with higher field, and what the material system which they have used are metallic multilayers. And in 1995, Professor Miyazaki and Professor Mudera, they have shown another kind of magnetic resistance effect, which is called tunneling magnetic resistance. In tunneling magnetic resistance, there are basically two ferromagnetic electrodes. In between, there is an amorphous oxide layer, and one can achieve 20 to 70% TMR in this material. Of course, after that, there are a lot of work, and people have shown very high enhancement of TMR. And this is basically the density of state variation near the Fermi level of ups and down spin, which is the basic physics behind that. So we thought that we can use our granular system for tunneling magnetic resistance measurement, because all our individual metal nanoparticles which are separated by insulating matrix could be one mini tunnel junction, and there are millions of such tunnel junctions on a sample. And in 1998, there was a paper published by Mitani, who in theoretical paper they have indicated such materials could be very good material for TMR. And we have done a series of measurement of various samples. However, we could able to see around 20% TMR at low temperature eventually decreases, and it happens because of spin flip scattering. Now we have used the shape engineered particles, and shape engineered particle shows a magnetic anisotropy. So if we look very carefully, that if we change the incident influence, what we observe, the out of plane coercivity, which is also an indication of the magnetic anisotropy, it peaks at a particular fluence of 5 into 10 to the power 13 nans per centimeter square, and it happens because the particles get elongated maximum at 5 into 10 to the power 13 nans per centimeter square, because after that the particles actually they get dissolved in the system because of very high incident or influence. So one can tune the magnetic anisotropy by this process. But what more interesting, what we have observed is what is called.
Gosh, I have to say this is your last minute.
Thank you. So what we have observed in exchange bias effect. So you can very clearly see that there is a shift in the loop, and this was simply explained because there is no core shell or oxide and ferromagnetic metal particle system. It is only after DFT calculation what we have seen that there is an intrinsic formation of antiferromagnetic domain because of that high temperature, and what we have noticed that it's a novel approach to trigger exchange bias, which is extremely important for magnetic storage. And we have also made a prototype based on this particle where one can see the out of plane resistivity varies with magnetization. This is a typical phenomenon of anomalous Hall effect, and this is much more sensitive Hall sensor, magnetic field sensor, as compared to normal Hall effect. So summarizing this, what we have discussed, the nanoparticle shape can be modified by ion beam, and we have discussed about field emission properties which can be highly enhanced for the shape modified particles. We have also shown some prototypes and magnetic tuning of magnetic anisotropy and exchange bias in shape modified nickel and iron cobalt nanoparticle, and we have also shown a magnetic field sensor. These are
Thank you very much.
Thank you. Any question, please?
Thank you very much. Thank you very much, Dr. Ghosh. We appreciate your nice talk. Now, the next speaker is Dennis Makarov from Helmholtz Center, Dresden, Germany. The title of his talk is Nanomagnetism and Spintronics of Thin-Film Magnoelectric Antiferromagnets. Okay, Dr. Makarov, are you connected? So then, if Dr. Makarov is not connected, may I ask my co-host Dr. Chi to play a video for him? Probably we have one.
Sure, I will play the video.
Thank you. He is the second speaker. Well, we can see the video, but no sound, but I guess it is what it is.
Magnetoelectric antiferromagnets. As you can see, we benefit from the broad network of collaborators who contribute to the sample fabrication, sample characterization, and also to the theoretical analysis of the effects which I will present in this talk. On the technological side, our motivation comes from magnetic random access memory. One of the possible classifications of families of MRAM is shown here. It depends on from which material you read out the information and how you write the information. For example, if you use ferromagnet to read out the information from and you use charge current to write the information, you will be in the realm of conventional magnetic random access memory, which is commercially available product. There is an antiferromagnetic counterpart of MRAM where you use charge current to write information in, for example, metallic antiferromagnet and read out the information from metallic antiferromagnet. Our work is inspired by the activities of the group of Christian Binek on the realization of magnetoelectric random access memory, where the magnetoelectric insulating antiferromagnet chromium oxide is interfaced with ferromagnet, and the magnetic state of the ferromagnet can be manipulated by the electric field which is applied across the antiferromagnetic insulating material. In our work, we removed the ferromagnet from the stack and ended up with antiferromagnetic magnetoelectric random access memory, where the memory cell contains only chromium oxide as a magnetoelectric insulator, which is interfaced with platinum readout electrode to access the magnetic state of the antiferromagnet. As many other groups in the community, we work with chromium oxide, which is the only uniaxial antiferromagnet which has magnetoelectric effect at room temperature. Already from 60s, it is known that this magnetoelectric effect is a linear magnetoelectric effect. It means that one can modify the magnetic state or the antiferromagnetic state of the material by the combined action of electric and magnetic fields. The very strong advantage of uniaxial antiferromagnet with an out-of-plane easy axis is the possibility to read out the magnetic state of the antiferromagnet unambiguously using conventional magnetotransport techniques. In this case, one has to monitor the field invariant transversal resistance after the sample was exposed to a specific cooling field or combined magnetoelectric cooling field. What you can see on this slide is a linear magnetoelectric effect in the thin film of chromium oxide, which is encoded in a Hall resistance, transversal resistance, which is measured on this material upon cooling the sample through the Néel temperature in magnetic and electric field. Such magnetoelectric cooling allows you to set up the antiferromagnetic state, and this state now can be manipulated, for example, by electric voltage at constant temperature, so isothermally, without any need to modify the magnetic field, which contributes to the application potential of this memory concept. What you can see on the left-hand side that for the specific conditions, also at room temperature, you can open the magnetoelectric hysteresis loop. You can get two remnant states, which allows you to record information in this thin film. The Mram operation is demonstrated in this slide, where you can use electric field pulses to write information into the chromium oxide. You can store the information in the antiferromagnetic order parameter and read out information using the platinum electrode. And you can repeat this for many times, mimicking the operation of conventional Mram. To enable such kind of measurements, we rely on a zero offset Hall preset of the tensormeter device, which allows us to reject any parasitic leakage of longitudinal resistances in the transversal resistance channel, meaning that we will have the pure transversal resistance, which is the quantity related to the antiferromagnetic order parameter of chromium oxide thin film. In order to understand the physics of the measured signal, we collaborate with a group of Sebastian Gönnenwein at the University of Constance. As you can see, we pattern our sample in Hall bar geometries, which allows us to measure not only the transversal resistance but also magnetoresistance when the sample is exposed to magnetic fields which are rotated in three orthogonal planes, as is schematically shown here. By analyzing the angular dependence of magnetoresistance, we can identify the clear fingerprints of the spin Hall magnetoresistance. Therefore, our current understanding is that the readout signal which we measure in a transversal and longitudinal channel below and above the Néel temperature of chromium oxide is related to the transversal and longitudinal spin Hall magnetoresistance in the platinum, which is interfaced with chromium oxide magnetoelectric insulator. Similar to the ferromagnet, the evolution of this electrical readout can be understood only if you have access to the magnetic domain pattern of the material. In the case of antiferromagnet, you need to image the antiferromagnetic domains, which puts very strong requirements to the sensitivity of the imaging technique. As you can see in this TM image, our thin film consists of grains with a size of in a range of less than 50 nanometers. And now the question is how the antiferromagnetic domain walls interact with the grain boundaries. What is the evolution of antiferromagnetic domain pattern with temperature, with magnetic fields? To answer these questions, we established a very fruitful collaboration with a group of Patrick Maletinsky at the University of Basel. They are experts in scanning nitrogen vacancy magnetometry or ENV microscopy, which they successfully applied to study antiferromagnetic materials. In the essence, the technique allows you to measure the magnetic stray field and magnetic stray field distributions over the surface of the sample. The blue and red contrast is a real space imaging of antiferromagnetic domains. What you can see is that domains are relatively large, a couple of hundreds of nanometers, which are substantially larger than the individual grain size, meaning that individual chromium oxide antiferromagnetic grains are exchange coupled to some extent to allow observing such kind of magnetic domain pattern. The strong advantage of ENV microscopy is that it provides you a possibility to access not only the quantitative stray field distribution over the sample, but also provides access to the magnetization of the sample. Now you can monitor the change of the contrast as a function of temperature. And in this case, you can get even access to the transition temperature from antiferromagnetic to paramagnetic state by determining when the contrast from the antiferromagnetic domain pattern disappears. In our case, this temperature is about 302 Kelvin, which is a couple of Kelvin smaller than the high quality single crystalline materials of chromium oxide. In order to understand what is the impact of the presence of defects like grain boundaries on the pinion of magnetic domain walls, we went back to the analysis of the very well-defined system. It's a single crystalline chromia with a C-axis and the Z-axis pointing out of plane. The quality of this material is very good, meaning that antiferromagnetic domain walls were not stable in these samples. In order to stabilize the domain wall, we patterned the array of mesostructures, as it's shown here schematically, on the surface of the sample and performed magnetoelectric cooling of the materials through the Néel temperature to impose the presence of magnetic domain wall, which is now pinned on one of these mesostructures. As you can see, the domain wall in the interior of the sample is actually a straight line, and only at the location of the meso it acquires a very interesting modification of the profile. You can obviously see and recognize such kind of a S-shaped profile at the location of meso. We performed theoretical analysis of this S-shaped curve and came to the conclusion that this is a pure geometrical effect, and the tilt of the domain wall at the edge of the meso is determined by the thickness to width ratio of the mesostructure. In this case, the tilt of the domain wall at the meso can be controlled by the geometrical parameters of the material. Another important feature comes from the analysis of the domain wall profile in the interior of the film. As you can see from the right-hand side image, the domain wall in the sample is actually flat. It's like a plane which is deformed only when the domain wall approaches the surface of the sample. If you have such a possibility to deform only the domain wall at the surface of the sample, then you have an interesting possibility to manipulate the domain wall and use it for some recording application. Please pay attention to this left-hand side image. The domain wall in the bulk is shown with a dashed line. It's the equilibrium position of the domain wall. Now you can use the laser light from the NV microscope to drag the domain wall from this equilibrium position and simply make it pin at the edge of the meso. There are two important characteristics which are recognizable in this image. First of all, the domain wall can be elongated substantially. It's displaced several micrometers, as you can see on this image. Another aspect is that the domain wall follows very precisely the very sharp edge of the meso. In this case, what you can tell about the mechanics of magnetic domain wall in chromium oxide, that it resembles something which is similar from the elastic ribbons. That would be an appropriate model how you can understand the behavior of the magnetic domain walls in this material. What is interesting is that you can use the laser beam in order to manipulate the position of the domain wall, achieving the stable pinning on one edge of the meso or on another edge of the meso, which enables interesting possibility to even consider such kind of elastic domain wall in a material as a possibility to write information by following how the domain wall follows the mesostructures which are patterned on the surface of the chromium oxide single crystalline material. The interaction of non-collinear textures with boundaries and with surfaces in antiferromagnets is actually very poorly understood even for three-dimensional antiferromagnets. In this case, Alexander Polipovsky made an effort to describe the impact of boundaries on chiral G-type antiferromagnets. In this case, the antiferromagnet has exchange, anisotropy and Dzoloshinsky-Mourier interaction in the material. Now what is happening if you have the ground state? The ground state for the case when DMI strength is subcritical is a collinear antiferromagnet in the interior of the material. As soon as the Néel vector is approaching the boundary, it acquires a tilt, and this tilt can be substantial. It depends on the strength of the Dzoloshinsky-Mourier interaction and can reach 10 or 20 degrees even for the realistic strength of the Dzoloshinsky-Mourier interaction constant. It's a sizable effect which should be observable in experiments. The qualitatively similar picture can be obtained also for non-collinear textures, where antiferromagnetic domain wall, for example, also gets modified upon approaching to this edge of the sample. It gets broader, the plane of the domain wall gets also modified, it acquires a tilt and also bend, and the direction of this bend is determined by the sign of the Dzoloshinsky-Mourier interaction. Qualitatively similar picture is observed also for Antipheromagnetics Kermions. For example, in this case, you have a Bloch-type Kermion stabilized in an antiferromagnetic slab. Upon approaching to the surfaces, the Kermion string becomes broader, and also the phase of the Kermion changing. It means that instead of Bloch Kermion like in the interior, you will have a mixed Niel-Bloch Kermion at the surfaces. What is important to mention that the main wall and the Kermion has a modification over several exchange lenses on each side. Therefore, if we want to work with the bulk-like properties of Kermion or the main wall, we have to make sure that the sample thickness and the sample width are sufficiently large, being at least in a range of 15 to 20 exchange lenses to enable the bulk properties of these textures. This is of course important for the design of antiferromagnetic racetracks, which are based on antiferromagnetic domains and antiferromagnetic Kermions as information carriers. At this point, I'm at the very end of my talk. Thank you very much for your attention, and I'm very happy to any questions which you might have. Thank you very much.
Okay, thank you very much. Nice video. I guess this is perfect timing. Our next speaker is Halite Kangas from VTT Technical Research Center of Finland. The title of the talk is Cellulose-Based Composite Materials for Additive Manufacturing in Electrical Insulation, Automotive and Marine Industries. Dr. Kangas, are you connected live? I don't see the name here. So may I ask then my co-host, Dr. Chichian, to play another video? Probably we have the video of Dr. Kangas.
Hello, participants of AAA-FM UCLA conference, and special thanks for the conference organizers for inviting me to give this talk. My name is Halite Kangas, and I work as a technology manager at VTT Technical Research Center of Finland. And today's presentation is about cellulose-based composite materials for additive manufacturing in electrical insulation, automotive, and marine industries. The co-authors in this work are Kirsi Immonen, Jarmo Ropponen, and Sini Metsä-Kortelainen, also from VTT. And before going into the actual topic of today, I will first briefly describe our affiliation, VTT. So VTT is a non-profit research organization located in Finland. We do applied research, so position ourselves somewhere between academia and the industry. And VTT is owned by the Finnish government and managed by the Ministry of Economic Affairs and Employment. Currently, we have around 2,000 employees working at different research fields in Finland. We all seen images like this and acknowledge that there is a real problem with the plastic waste. And VTT's approach to tackle this plastic challenge is to reduce and replace the amount of fossil-based materials by innovating novel materials from plant-based resources. We will also take into account recycling of these materials and reuse of them according to the circular economy principle, and pay special attention to biodiversity. And one of the focuses is use of cellulose. And why would we use cellulose-based materials for additive manufacturing? Well, cellulose is abundant. It can be found in all plants in nature, and it's sustainable and versatile material with unique inherent properties. Cellulose has been used as a raw material for additive manufacturing and has been found suitable for it. And of course, when using cellulose as a renewable raw material, it's possible to reduce environmental impact. And also it enables the use of local raw materials. Additive manufacturing itself enables the moldless production. So when producing or manufacturing components, mold is not needed. Also promotes regional and distributed manufacturing, and there is a possibility to reduce the material waste. So all material that is used in the manufacturing, it will go into the actual product. And of course, there is a challenge that cellulose is not naturally thermoplastic, so it cannot be used for additive manufacturing as such. And this challenge has been tackled in the project that I'm now describing. So the project where the results of this presentation are coming from is called, the acronym is NOVUM, and the full title is Pilot Line Based on Novel Manufacturing Technologies for Cellulose-Based Electrical Insulation Components. It's funded by the European Commission's Horizon 2020 framework program. And the total duration of this project is 54 months, so 4.5 years. And currently we are on the last leg of the project. So, and this project will end in March 22, next year. And currently we have 9 partners from 5 European countries in the project. So we have partners from Finland, Poland, Germany, France, and Italy. And the Novum is focusing really on additive manufacturing of cellulose-based thermoplastic materials. And there are different end uses. So we are looking into electrical insulation components represented by partner Hitachi ABB Power Grids. For automotive components represented by Research Center of Fiat Chrysler, CRF. And for decorative elements in cruise ships, represented by Meyer Turku, which is a shipbuilding industry located in Finland. We are also looking at printing of fiber foams into 3D shapes and for insulation purposes, but this research line is not under discussion in this presentation. And the outcome of this Novum project, as the title also said, is a pilot line for this component manufacturing. So it will be based on the developed additive manufacturing technology and for the different end-use purposes shown above, and using the cellulose-based material developed in the project. So first, a few words about the cellulose-based material development. The materials developed in Novum thus far, we have developed roughly 30 different compositions. And these composite materials are based on cellulose, acetate propionate, and microcellulose, with a small amount of bio-based plasticizer if needed. And the material strength properties are at the same level or even better than the commercial references, which are usually PLA-based. And in this, our material compositions, PLA is not used. They have a higher cellulose content compared to commercial references, so we can reach the total cellulose content of around 50 to 60. And they are potentially 100% from renewable resources, so no fossil-based materials used here. They have demonstrated excellent 3D printability, producing light and smooth surfaces in the products. And the printing process is safe. There is no gas or bad odors generated if the moisture content of the material is below certain limit. These materials are recyclable ready, meaning that they can be, after printing, the components can be crushed and granulated and printed as such again. And we have studied that the material properties are not deteriorating up to 8 cycles. And these developed materials are also suitable for injection molding, which means that this kind of it extends the possibilities for their use. We have faced some challenges in layer adhesion and required mechanical properties for certain end-use applications, but these are now being considered in the project. Here are some exemplary images of the materials that we have developed. So they can differ in color. Depending of the composition, they can be in the form of granules or filaments and printed as such. And here are some examples of the kind of components that have been printed with those. So there is this, as an example, this lampshade, and also a very small mock-up of electrical insulation component. And this material composition is currently under patenting. Here are some mechanical properties measured both from the component that has been manufactured by injection molding and by 3D printing or additive manufacturing. So, and if we compare the novum materials, there are 5 examples of those. They are comparable or better than the kind of the mechanical properties of commercial references, meaning, for example, this form Futura. Some mechanical properties are better and some are a bit lower. For example, this modulus is something that we still face challenges compared to commercial references. More details can be found from a recent publication where the reference is shown in the slide bottom. Then a few words about the technology development for additive manufacturing. This work has been done by our project partner Printer, and they have this registered trademark for their equipment. So the additive manufacturing of thermoplastic cellulose-based, after a throughout review of the different additive manufacturing method, a fused deposition modeling was selected as the printing method. And this printer concept developed is suitable for the granulate material, and this gives us a kind of edge compared to competitors, which are usually using filament printing. And the developed printing technology and the developed novel materials will be used at the pilot line, which is under construction now. And then also this potential upscaling to meet the end user requirements in terms of size, shape, and different dimensions is also considered here. And this 3D technology development, it has been taken place in phases. So in phase 1, there was the concept design test and verification. First, a modular, scalable, and multi-material capable desktop unit was developed using multi-material printing tools. And of course, then in phase 1, it was kind of this production line capable system was developed with using granulate printing tool. And then, of course, after that, different post processes, quality control, etc., as well as the scaling, the printing size and speed were considered. And in the end, we are having or pilot line capable large scale industrial system to be put up at the pilot line. And the main key technical drivers for the work within this project has been the granulates and foam, thermoplastic granulates and foam as the printing material. And for the thermoplastic materials, we wanted to consider the possibility to use the recycled material, crushing and granulating without the need of compounding. And this was then established. And also we wanted to consider multi-material printing and hybrid manufacturing possibility with up to 4 heads. For example, different printing head size and using solid and foam type of materials, even producing this sandwich type of materials where you could have a solid outer surface and then foam type materials in the core. And also to kind of tackle the challenges with the different sizes and shapes and so forth we needed, and the layer adhesion, we needed this heated pallet and conveying system to enable production at larger pilot line scale. And with this, I would like to thank you for your attention, and my contact details are here in case you have any questions for me after this presentation. And also would like to mention that this work has received funding from the European Commission Horizon 2020 program with the proposal Novum. Thank you very much for your attention.
Okay, wonderful. Our fourth speaker is Dr. Pinar Çevik from Gazi University, Ankara, Turkey, and she will speak about PEEK, a high-performance polymer used as patient-specific implants. And I see Dr. Çevik live, so just test the sound, please, the connection, and share screen, and you are ready to go.
Okay, thank you, Professor Chichi. I'm here, and hello, everyone. Can you hear me?
Yes, we can. Just share screen, please.
Okay. Hello, everyone, again. I am Pinar Çevik. I am an associate professor, clinical associate professor at the Department of Prosthodontics at Gazi University School of Dentistry, and my co-author is from otorhinolaryngology, head and neck surgery at the same university. Today, I'm going to describe our patient who underwent a mandibular reconstruction and give some general information about the general properties of PEEK material. I've just selected our most recent case and only one case because of the time limitation, of course. And I've selected this case because to the best of our knowledge, this is the first case of application of one-piece additively manufactured PEEK mandibular implants prosthesis with intraoral abutment parts and without a fossa part for the condyle of the temporomandibular joint. So let's take a look at PEEK materials briefly. PEEK materials, commonly referred to as PEEK or PEG, belong to the class of high-performance engineering polymers and have been introduced as alternatives to metal alloy and zirconia for implant frameworks in medicine. The melting point is PEEK is 335 degrees centigrade, and the tensile strength is about 80 megapascal. And the elastic
can you please check if you share screen, because we see you in video but we don't see the shared screen. Something
really?
is going.
Okay.
I'm not sure what's going on. Yes, now it's better. Yes.
Okay. Okay. Thank you. Thank you. And yes, the elastic modulus of PEEK is 3 to 4 gigapascal, which is very close to cortical bone as compared to titanium alloys, as you can see here. And also the modulus of PEEK structures can be altered by incorporation of carbon fiber reinforced composites with varying fiber length and orientation. For decades, titanium and its alloys have been the first choice for the fabrication of implants. However, galvanic corrosion associated with metal structures is a common problem for titanium and its alloys. Furthermore, more stress points can occur due to the gradient difference in the elastic moduli of the titanium implant and the adjacent bone, leading to resorption of the surrounding bone. This is the main disadvantage of titanium or metal alloy, metal-based implant structures. And metal-based implant structures are associated with some issues such as metallic color, metallic taste, and allergies. On the other hand, lack of ductility, chipping, and cracking may be seen on the ceramic-based implants. Thus, polymer-based materials became popular for use as implant biomaterials. Apart from the mechanical properties, we have to say some biologic properties of PEEK structures as a biomaterial. Studies shows us the biofilm formation on PEEK implant structures were lower than that on zirconia or titanium implant components. In addition, mucosal response to PEEK as an implant material was found good. And it was also reported that PEEK abutments can withstand intraoral masticatory forces similar to that of titanium implant structures. And you can see the PEEK properties here. PEEK is a thermoplastic semicrystalline high-performance polymer, and these properties make PEEK a favorable implant material for its use in the medical field, in medicine and dentistry. PEEK can be implantable to the alveolar bone as far as it can be used as a framework material for titanium dental implant substructures. In prosthodontics, we can use PEEK as a superstructure and an main implant body as well. Patient-specific implants can be designed to match the mirror the anatomy of the contralateral unaffected site. The success rate of patient-specific implants and patient-specific surgical cutting guides is also high. PEEK has a great potential as using patient-specific implants in the field of medicine and dentistry because of its biocompatible properties. Recently, patient-specific implants are common due to their best-fitting components with anatomical structures. Computer-aided design and computer-aided manufacturing, namely CAD/CAM, has become a part of fabrication of patient-specific implants. CAD/CAM can be considered as an umbrella term that includes subtractive method, namely milling, or additive manufacturing, known as 3D printing. In subtractive manufacturing, CAD/CAM systems use milling, drilling, or grinding techniques, which are based on removing or cutting materials from solid blocks or bars. On the other hand, 3D printing uses layer by layer technique, which is environmentally friendly. And 3D printing causes low waste materials. PEEK can be fabricated by both subtractive and 3D printing methods. Recently, PEEK patient-specific implants mostly are fabricated by subtractive methods, such as skull-based implants and zygoma implants, or dental implant structures. You can see right here. Dental CAD/CAM milling machine on the PEEK blocks. And on the other hand, patient-specific implants should fit the anatomy, so patient-specific implants require complex design, which should be fabricated by 3D printing. PEEK is a high-performance biopolymer with an elastic model very close to the bone. It allows the distribution of stress in the tissue it is located in, and it's successfully used as implant and superstructure material in the fields of orthopedics, plastic surgery, maxillofacial and oral surgery, and dentistry. Today, standard or personalized implant systems are usually produced from titanium or cobalt chromium alloys. It is known that metallic implant systems scatter X-rays in imaging, in radiographic follow-ups in malignant cases. This makes difficult to follow up the tumor site. It is the most important part of our site. So radiolucent high-performance PEEK implants have become popular recently. Now let's take a look to our case. A 20-year-old female patient was referred to the Department of Prosthodontics for a need of a dental prosthesis. She previously had a hemimandibulectomy induced by ameloblastoma. The defect site was extending to the condyle. The patient previously underwent an autologous bone graft harvested from fibula in the plastic surgery department. However, the first concern of patient was the asymmetry resulted from hemimandibulectomy. You can see the CT images from the frontal and the lateral sides of the patient. After consultation to head and neck surgery department, a reconstruction of the mandible was planned. Because of the graft failure history, a second autologous graft operation was avoided. Thus, an alloplastic patient-specific mandibular implant was planned for the patient. First, skull of the patient was scanned in CT, right here, for modeling and getting mirror image of the healthy side of the mandible. These processes were conducted digitally according to CT images of the patient. CT images were then exported to a software program, which is called 3D Doctor. This software program is a 3D modeling, image processing, and measurement software. After initial modeling at this program, working models were additively manufactured from PLA material by an FDM 3D printer. Thus, a patient-specific mandibular reconstruction implant was designed from the mirror image of the contralateral healthy side of our patient. The fabrication process, you can see the fabrication process right here. And the final peak mandibular implant with condyle part and the ramus part with intraoral abutments. In addition, 3D design of the surgical cutting guide was also designed on the same software program for our patient. The surgical cutting guide was fabricated from dental resin PMMA materials. This cutting guide was later used for the cutting the screw holes on the mandible during the surgery. A one-piece peak implant was additively manufactured by layer by a 3D printer. Screw holes for lateral pterygoid and masseter muscles, right here, lateral pterygoid and masseter muscles was designed and fabricated on the implant. And implant was sutured around these holes to the muscle ligaments during the surgery. After insertion, the implant radial forearm free vascularized flap was sutured to the defect site intraorally. We should talk about FEM, finite element modeling for initial design processes in such implants. Patient-specific implants. Finite element modeling provides biomechanical information useful for final patient-specific implant shape and loading areas. But we cannot use any statistical analysis methods at FEM. Mostly the aim is to carefully examine and interpret the obtained values and stress distributions via FEM. It's very important to evaluate the data obtained in the most accurate and reliable way in terms of the clinical results to be reached at the end of the clinical studies. In our case, we used a static linear analysis using three-dimensional finite element stress analysis method to examine stress values, stress distribution, and concentration regions. You can see the models. First, we designed an additional titanium plate at the anterior side of the patient, for the patient. At the left side, you can see no titanium plate and the mandibular implant fabricated from PEEK and the finite element model. At the right side, you can see FEM with using an additional titanium plate. As seen at the right side, stress concentrations were high on the titanium plate. So we didn't use any additional titanium plate on the anterior side. First, 3 horizontal and 2 vertical screws, as you can see here, were designed for this patient. However, after evaluating the FEM results, we changed the design and we designed 4 horizontal screws and 2 vertical screws for this peak implant. Of course, this FEM was conducted under the function of lateral pterygoid and masseter muscles bilaterally. FEM offers a big advantage in terms of changing the total design of a patient-specific implant at the initial step. As I said before, this allowed us making corrections and making some modifications on the final design and so final fabrication of the prosthesis. In our case, FEM was conducted on peak implants, implant screws, and the alveolar bone of the healthy side. In this case, 3D design also allowed us eliminating possible screw overlap inside the alveolar bone. Screw directions were adjusted with the aid of 3D design. Due to maxillomandibular tumor surgery, the chewing and swallowing functions of the patients decrease and the quality of life decreases. Although resection repairs can be performed with autografts, the success rate of autografts is low in complex anatomical points of wide resection areas. We described here a rare complicated case of amyloblastoma that required complete resection with temporomandibular joint extended hemimandibulectomy. A one-piece patient-specific peak mandible implant was designed and fabricated. Peak implant was inserted into the patient's mouth under general anesthesia. The initial results are satisfying. Of course, I cannot share the detailed surgical parts of the patient. And future midterm and long-term results will also be discussed. And we are preparing the manuscript for the publication. In conclusion, the following advantages of PEEK. Because of the following advantages of PEEK, we used an alloplastic PEEK implant material for our patient. Excellent dimensional stability, high mechanical properties, high temperature resistance, and high comfort due to the immediate absorption of body heat, no metal allergy or no metallic taste, no X-ray scattering, which is very important for us for tumor follow-ups. And it's the pure material, no additives, no coloring, no abrasion, all antagonist. And we would like to thank to medical design company iTasarım and Mr. Ayberkios for FEM, 3D design, and 3D printing of PEEK implants. Thank you for you all for listening. And if you have any question.
Okay, thank you, Dr. Čevik. We appreciate your time. So great.
Thank you.
Thank you. Okay, our next speaker is Dr. Martin Schmidbauer from Leibniz Institute in Berlin, Germany. And the title of his talk is Ferroelectric Phase Transition in Strained Epitaxial Films, studied by in situ X-ray diffraction and three-dimensional phase field simulations. So do we have Dr. Schmidbauer live? I don't see his name. So as I did earlier, let me ask my co-host, Dr. Chitchan, to put the video of Dr. Schmidbauer.
Gentlemen. Good morning, ladies and gentlemen. Today I would like to talk about ferroelectric phase transitions in strained potassium sodium niobate epitaxial films studied by in situ X-ray diffraction and three-dimensional phase field simulation. So this is actually a collaboration between our group at the Leibniz Institute für Kristallzüchtung in Berlin, Germany, and a theory group from the Pennsylvania State University who have performed the three-dimensional phase field simulations. Let me first start with the material system potassium sodium niobate. It's a lead-free perovskite-like material with promising ferro and piezoelectric properties already as bulk material. It exhibits high Curie temperatures, but has been hardly studied as film material so far because of the high volatility of the sodium and potassium, which may lead to defects and high leakage current. In order to overcome this problem, we have performed metal-organic vapor phase epitaxy, MOVPE, which is carried out at high partial oxygen pressure, close to thermodynamic equilibrium, at typical growth temperatures around 700 degrees centigrade. And this highly sophisticated growth techniques leads to very perfect, coherently strained stereometric films with a very regular ferroelectric domain pattern. And as a typical example, I show on the right side a lateral piezo response force micrograph of a 30 nanometer thin film grown on neodymium scandate substrate. And you see here a very regular herringbone domain pattern. And this high periodicity is a direct proof of the high perfectness of the thin film. So we are interested in phases and phase transitions in our thin films. For bulk crystals, the parameter for phase transitions or for phases is the temperature. However, for thin films, it's not only the temperature, it's also the epitaxial misfit strain incorporated in the thin film. And in the middle of this transparency, the so-called temperature misfit strain phase diagram is shown, where depending on temperature and strain, different ferroelectric phases may appear. For example, close to room temperature, we see a mixture of the monoclinic MC phase and the monoclinic A1, A2 phase. And it would be nice to experimentally prove the existence of these monoclinic phases, in particular to prove the existence of this mixed regime at room temperature. And the other question is, can we identify and study a phase transition at high temperature, and how does this mixed regime change at high temperatures? Okay, so at this slide, I will first start at room temperature. You see here at the left side experimental evidence or experimental proof of this mixture. We indeed find a model where we have a coexistence of MC monoclinic phases and A1 monoclinic phase. So the MC phase is shown on the left side top. You see the unit cell where we have this shearing, and the polarization vector lies within this plane of the unit cell and is inclined. On the other hand, when you turn this unit cell by 90 degrees such that the polarization vector lies now in plane, we end up with the A1, A2 phase. And you see now that the herringbone pattern is composed of a regular arrangement of these MC and A1, A2 phases. And you see this already also at the right side with the lateral piezo response force micrograph. And the very nice thing is now that when you perform three-dimensional phase field simulations, you end up exactly with the same model. You also here see the herringbone pattern consisting of MC phases, which are shown in the and the A1, A2 phases shown at the bottom as pink and violet colors. So we have a very, very nice agreement between theory and experiment. So what will happen now at high temperatures? So when we heat up the sample and let's heat up the sample and look at the PFM images. First I have to say, when you measuring PFM at high temperatures, you have to use a rather robust cantilever, somehow reducing the experimental spatial resolution. So when you look at the left side, you do not see the herringbone pattern as good resolved as I have shown you already before, but this is the herringbone pattern we see here. So when we heat up to 180 degrees C, nothing has changed. Of course, we see some thermal drift, but when you further heat, let's say up to 250 degrees centigrade, you see an abrupt change of the domain pattern. So you see here a striped domain pattern. So we really observe here ferro to ferroelectric phase transitions within the temperature range of between 180 degrees C and 250 degrees C. However, as you know, PFM does not give you any information about phase symmetry. In order to get this information, we have performed three-dimensional in situ X-ray diffraction. So why three-dimensional? Because on one hand side, the strains themselves are three-dimensional in their nature. We have in-plane strains, we have out-of-plane strains, we have shearing in different directions. So this is all 3D. On the other hand, the domain morphology, so the arrangement of the domain walls, is also 3D. Therefore, we have to measure the intensity distribution in reciprocal space in all 3 dimensions. In order to do this in a rapid way, we have used a 2D detector, and then it goes so fast that we can even do in situ investigations, because one 3D reciprocal space map does not take too much time. Of course, for these studies, we need a very intense X-ray source, so we have to do all these experiments at synchrotron radiation facilities. And at the bottom, you see 2 experiments, exemplarily one at BESI-2 at the left side, and one at the IO7 beamline at the Diamond Light source in UK. And you can distinguish, you can do now really true 3D out-of-plane coplanar X-ray diffraction, but you can also concentrate on grazing incidence in plane X-ray diffraction, where we have only investigated this in 2 dimensions. And the first example is now when you measure now the diffraction pattern at different temperatures. At room temperature, you see a typical fingerprint of the herringbone pattern. You see the peaks P1, P2, which arise from the A1, A2 phase. And you see the peak P3, which arises from the monoclinic MC phase. And when you heat up the samples to high temperature, we see a change in the diffraction pattern, indicating that we have a structural phase transitions at these high temperatures. When you further heat up the sample, you end up with the paraelectric phase at about 500 degrees centigrade. So in order to investigate now the crystal symmetry at these high temperatures, we have to measure a set of different pracrefactions, because we have to disentangle different features in this diffraction pattern. One is, for example, the peak splitting caused by the phase symmetry, P1, P2, P3, for example. The other hand is we have strong satellite peaks caused by the very perfect domain periodicity. And for that reason, we have to and in order to get information, we have to set our model in real space. In this case, we have set up 4 different orthorhombic unit cells, which are slightly rotated in different orientations, ending up in 4 different variants of A1, A2 stripe domain patterns. And when we put this model into numerical X-ray simulations, we end up here at the left side, to the bottom, we see these 4 simulations, and they fit quite nicely to the experimentally observed diffraction pattern. So indeed, we have at high temperature a slightly rotated orthorhombic phase. Okay, we can compare this also now with phase field simulations. And on the right-hand side, we see that also in the 3-dimensional phase field simulations, we observe orthorhombic phase with A1 and A2 unit cells, and we observe, by the way, also different stripe domain variants, quite similar to the variants we observe in the PFM image in the middle. So we have a very good, or an overall good agreement between simulations and experimental data. So far I have shown you only experiments performed in 2D, so in plane. But what is now the 3D domain wall arrangement? For that reason, we have performed true 3-dimensional X-ray diffraction in order to determine the 3D arrangement. So you see here on the left side a 3D diffraction pattern, which took only 30 minutes. And we see here 4 prominent streaks coming from the domain wall. So we have 4 different domain walls, and in order to make it more clear, I have made now in-plane and out-of-plane sections at the right side of the transparency, and you can directly compare this now to three-dimensional phase field simulations. And they again perfectly fit. So for example, the in-plane herringbone angle Xi is reproduced. It gives us 20 degrees, also in the phase field simulations. But more importantly, also out of plane, you see domain wall angles of plus minus 45 degrees in the experiment. And this is also exactly reproduced in the phase field simulation. So again, a very, very nice agreement. You can do the same thing now for the high temperature phase. Again, see a very rich diffraction pattern, and you can do again in-plane and out-of-plane sections. In the in-plane section, you see a cross-like behavior, and this cross comes from the stripe domain pattern, which are oriented 90 degrees to each other. So the angle Xi is plus minus 45 degrees. More importantly, when you look at the out-of-plane section, you see the intensity distribution, which is aligned in the horizontal direction, proving that the domain walls are oriented vertically to the sample surface, and this is exactly what you observe in the phase field simulation shown below. So again, a very, very good agreement between theory and experiment. So, but how exactly does now the phase transition take place? And for that reason, I've shown you now a true temperature series between room temperature and about 260 degrees centigrade. On top you see the phase field simulation, and the bottom you see the corresponding X-ray data. And we start at the top left, you see the simulated domain pattern with the A1, A2 and MC domains. This is reproduced in the X-ray data. You see the peaks P1, P2 coming from the A1, A2 domains, and you see the peak P3 originating from the MC domains. When you heat up the sample a little bit, nothing seriously will happen. But when you go to the middle of this X-ray data at 180 degrees C, you see that only the peaks P1, P2 are preserved, while P3 has vanished. So the MC phase has vanished, and this is exactly what we observe in the simulation. You see here at 227 degrees in the simulation.
Since the time is up, may I suggest to my co-host to stop the video here? Everybody can watch it in YouTube later on, or will be uploaded there, and then we move on to our next speaker that I believe is live, and he is Dr. Albert Wang from University of California, Riverside, who will speak about using graphene-based devices and interconnects for IC reliability. Dr. Wang, are you there?
Oh, sure, I'm here.
Okay, wonderful. Then you know what to do, I guess. Check the sound, microphone, and share screen.
Sure, thank you, Oren. Let me first share my screen and make sure the slide can be shared. Okay, so do you see my slide in the presentation mode?
Yes, we do, and you can make it full screen, and now it's just fine. Yep.
Oh, I already made it full screen. So what do you see? You see the presenter's view, or you see the? I have two screens.
Well, we see your first slide using graphene-based title, authors, etc.
Yeah, it's a first screen, or
yes.
It's
yes.
Oh, okay, okay, good. Okay, I try to. Okay, so good afternoon from California. My name is Albert Wang. I'm professor of electrical and computer engineering at the University of California, Riverside. So the title of my presentation is using graphene-based devices and interconnect for integral circuit reliability. So as suggested by the title, it's a little bit different from the other presentation. So this presentation is not about materials research itself. Instead, it's about how to use this graphene 1D or 2D materials to make devices to protect integral circuit. So this work was done by my student and who made the device and the integral circuit. And the materials part, the graphene, was prepared by our collaborator at UCLA. Another thing I want to make out is I want to point out is this is a review paper. It's not reporting anything not published yet. It's a review paper. Okay. So here's the outline. I start with the introduction to ESD protection. So ESD stands for electrostatic discharge. And then I start talking about graphene-based GNAMs. It's the NAMs, we call the graphene NAMs, so we named GNAMs. It's a GNAM switch for ESD protection for IC. And then the next topic will be graphene-based interconnect for ESD protection for IC. And I will give a future perspective about ESD protection for IC and end up with a summary. Okay, so we all use a smartphone. The majority of them are actually touch phone, right? So when we play when we touch the screen mainly every day, every second, and something bad could really happen because a human body will have some electrostatic charge accumulate. Apparently, depending upon the body size and the location, whether or not it's dry or wet, or whether or not you're happy or mad, right? So the thing is, when you touch the screen, and those static charges are inside your body will start to discharge into the smartphone. That can immediately damage your smartphone, and that will cost $1,000 for now, probably, right? So apparently, the only reason that we can use smartphone without worrying too much of things because we have some kind of protection measures in place, and this is something I want to discuss today. Okay, so what about the ESD philia and the ESD protection? As I mentioned, the electrostatic charge inside the human body can discharge into any electronic device. The phenomenon is it will generate a huge current pulse, and that current pulse we are talking about the level 2 amp level, and that generates a lot of heat inside the integral circuit and actually all the electronic equipment over there, and that may cause thermal damage. Another phenomenon is there's a huge voltage spike over there that will generate transient very high level electric field density, and that will create some dielectric breakdown. So those are the problems we have to worry about. And with that, as I understand it, we need to have some on-chip ESD protection for integral circuit. Now, as illustrated at the lower left-hand side over here, so a chip will have many ESD protection devices connected at all the input, output, or supply path over there. So from external world, when a static charge trying to get into the integral circuit, some of the protection device will be turned on. And if that happens, it will form a low impedance conduction path to discharge the incoming electrostatic charge into the ground so that the internal circuit will be protected. So this is general concept. But this ESD phenomenon is very complicated, so that each IC will have a very complicated ESD protection network. And you can see one of the huge problem over here that will be that is that ESD protection structure. There are so many of them. Each of them are very large, and it takes a lot of the silicon die area. In other words, it will make your iPhone more expensive. Okay. Now, how it works? On the right-hand side, the IV curve shows the ESD protection discharging behavior. It can be either like diode or a snapback IV, meaning during normal operation, the protection structure will stay off. But when the voltage reaches to a certain level, the protection device will be turned on. And it behave like a switch and then discharge all the static charge into ground. So it can be either very simple diode-like IV turn on or SCR type of silicon controlled rectifier type snapback IV curve. So this is a general concept over here. So far, for almost more than 50 years, people have been using the PN junction-based electron device inside IC chip to do the ESD protection. So those devices can be P plus N diode, N plus P diode, any kind of MOSFET transistor or BJT transistor, or the SCR, silicon controlled rectifier. So those devices looks nice, but they have a major problem. In addition to, I just mentioned, it takes a lot of die area, making your IC layout extremely difficult. The other problem is those built-in PN junction has an inherent leakage issue, noise issue, parasitic capacity issue that will affect your IC chip. So especially today we're talking about 5G communication or next generation 6G communication, any kind of ESD induced parasitic effect will kill the IC chip. So apparently we need something really, really new. Now this comes to the graphene application over here. So from the previous discussion, you can feel like I have a few required features needed for ESD protection. Electrical conductivity, I want the mobility high so that discharging resistance will be low. Thermal conductivity, I want the heat generated can be discharged, dissipated to the outside of the chip efficiently. I want the device really, really robust, really strong, mechanically strong. So all those things actually are good features of graphene materials. Super mobility, super thermal conductivity, and high melting temperature, as well as the mechanical very tough, and also the strong Young's modulator makes it really, really fast. So it will respond to ultra fast signal. So based on that understanding, we devised two concepts using using graphene for on-chip ESD protection IC. Now the first one is just the name switch illustrated over here. So basically, there is a cavity over here. We have graphene membrane on top of the cavity serving as one terminal, and then the bottom silicon will be the second terminal. The two terminal device can be connected to the integral circuit at the signal pad or the bias pad over there. So as incoming ESD pulse coming over here, the graphene membrane will start to be pulled down until it touches to the bottom one. So the complete open structure will become a short circuit, and then it starts to discharge the static charge over there. So this is how it works. Nicely, this can be symmetrical, but not as illustrated over here, because the structure in the prototype by itself is not symmetrical. So you will see the measured data is slightly asymmetrical now. Okay, so another very, very nice feature is the device, the graphene, the GNAMS device is not inside silicon. It's actually placed on top of the silicon in the so-called back end of line, BEOL deck over there, where you have the complex metal interconnect for IC state. Okay, so this is another major feature. That means the ESD, graphene ESD structure will not consume the silicon area. So this is another big feature. Of course, because it's outside the silicon area, and then it will not introduce a lot of PN junction-based parasitic effect like the noise, leakage, parasitic capacity, and so on and so forth. Now, let's see how it works. So this is the CMOS compatible process we developed, starting with the wafer, putting up some silicon dioxide and then silicon nitride, and create the opening over here, and then transfer the graphene, and then use HF to etch the silicon dioxide underneath from the cavity, and eventually you will have this graphene GNAMS structure. And this is shown from the image over here. You can see two pads over here, and then the graphene ribbon is this one over here, and the little darker one underneath is actually the cavity over there. So let's see how it works. So we start to do the characterization using the very fast transmission time pulse testing, which is the square wave. The square wave has duration TD and the rising time TR. We first start, we did a lot of structure with different dimensions, the graphene ribbon length and the width and the cavity depth over there. So first the DC, showing that it did showing up diode-like turn-on. So with different structure dimension, you can see the turn-on voltage is different. The turn-on voltage we call BP1. And then we did the trending TRP testing. You can see it's turned on and it's also almost perfect symmetrical. But the device we manufactured was not symmetrical by itself. So you see the little asymmetrical feature over here. Okay, so a little further characterization. We tried all the different dimensions. You see the current handling capability versus the graphene ribbon length, and also trigger voltage versus the length. You can see at the length, graphene length increase, the trigger voltage decrease a little bit because it's kind of losing over there. And we did not expect the current density change. However, we did measure that. That was probably because the graphene film that we use is not perfect, probably. Okay, so we also measured the trigger voltage and the current versus the graphene width over there. You can see the difference over here. And one of the key things is you can change the characteristic by changing the device dimension over here. Say the trigger voltage change, and it reached the probably the highest reported current density 10 to 8 amp per centimeter square. Several others higher than any silicon device over there. So I'm running out of time. Just quickly about another topic. Let's use the graphene ribbon for interconnect between the IC pad and any type of ESC protection structure. We did a lot of characterization and showing some very interesting results. First of all, IV measured by TRP showing the breakdown for voltage and current over here. So this is a graphene current handling capability over there. And then we shows the breakdown voltage and the current versus graphene ribbon length and width over here. And more interestingly, we actually showing the temperature behavior. When you do the thermal annealing, you actually see the bear-shaped kind of the curve. So that sort of means you can optimize the design through manufacturing technique over there. We also showing the monolayer and the bilayer. Basically, it shows a bilayer can conduct more current compared to the monolayer. Now, one last thing I want to mention is you can always improve the materials. What we show is the device made of a polycrystalline graphene versus the single crystalline graphene. So the poly one is over here is this one, and single crystalline graphene is over here. If we extract the current handling capability in terms of the current density, you can see that clearly the single crystalline graphene is much tougher than the polycrystalline graphene device over here. So with this, I want to basically conclude my talk. So this opportunity completely changed the way you design ESC protection for IC. You put all the graphene-based switching device as ESC protection on top of the silicon, and this gives you a lot of flexibility for future IC chip design. So in summary, we devised a new graphene-based NAMS switch along with graphene interconnect structure to provide on-chip ESC protection for integrated circuit, which will also apply to all the electronic systems. And this is a very exploratory research, and it will take a lot of effort in materials optimization. So with this, I'm done. Thank you. I think
okay. Thank you, Dr. Wang. Thank you, Dr. Wang. We appreciate your talk. So Next speaker is Dr. Paweł Malinowski from Polish Academy of Sciences, Poland. His talk is about damage assessment of composites using techniques based on guided waves and electromechanical impedance. So is Dr. Malinowski present? I don't see him, so we can safely play the video. I presume we have it.
Good day. Thank you for attending my presentation. My name is Paweł Malinowski, and I will be talking about damage assessment of composite structures. This work was prepared in collaboration with my colleagues, Dr. Soman, Professor Kudela, Professor Wandowski, Mr. Singh, and Mr. Balasubramaniam. We all work at the Institute of Fluid Flow Machinery, Polish Academy of Sciences in Gdańsk, Poland. My presentation is structured as follows. First, I will introduce you to the subject, give the motivation, present the guided wave-based method and the electromechanical-based method. At the end, I will summarize my talk on one slide. We are looking for damage identification and assessment methods in order to prevent failures of various structures. Here are some examples of damaged structures such as rail track or broken wind turbine blade. I would like to prevent such events due to early detection of damage such as cracks, delaminations, debonds, and so on. Some of the promising methods used for this task are based on guided wave propagation and the electromechanical impedance. The damage assessment falls into the broader scope of so-called structural health monitoring. The structural health monitoring concept uses a network of sensors deployed on a structure. Next, signals from such sensor are gathered, processed, and at the end you would like to know if the structure is safe to use, so-called healthy, or is it unsafe, is damaged and needs repairing. The focus of my talk will be structures made of lightweight materials such as aluminum alloys, Cfrp and Gfrp composites. During the research, we need to answer few questions that are related to the structures that we are investigating. So, where to place the sensors, how to effectively excite the structure, or how to take advantage of external excitation such as wind, or how to process and assess the data in order to get information about the damage, presence, its location, and also severity. The first method that I would like to introduce is the guided wave-based propagation. Guided waves are the elastic waves that propagate in thin-walled structures. They propagate in multi-mode nature, so we have so-called antisymmetric modes and symmetric modes that propagate with various velocities in the material, and depending on the frequency we can have more than one mode propagating in a structure. So at the defect location or at the other discontinuities, such waves are scattered and are also reflected and converted to other modes. So in the figure on the left, it is showed how the propagating symmetrical mode S0 is converted to the antisymmetrical A0 mode, both at the damage and also at the edge of a simple square-like structure. In order to inspect structures, various sensor networks and arrays are used. Here are a few examples. The concentrated arrays that work like radars to scan the surrounding area, or there are also distributed networks that are based on placing sensors far away from each other in network nodes to cover large areas. There are various attempts to put such sensors on the surface, like triangular networks or double sensor networks, where in each node there are two sensors placed. Another effective way to sense the elastic wave propagation is the laser vibrometry. In this approach, the laser beam scans the surface of an object and senses the vibration of a surface. In this way, propagating waves are gathered and such signals are processed in order to assess the damage condition of a structure. Having set of registered points, here we have n points gathered as an example. We can visualize the propagation of the wave. Later, such results can be processed. It can be represented in the so-called energy representation, and then some discontinuities that were encountered by the wave propagating the structure can be visualized. Here we see few scatterers of a wave present in this example. On the right hand side we have the frequency wave number representation that allows us to see how the wave number and wave phase velocity changes with the frequency in the investigated material. Some other examples of wave propagating in structures. So here we see some interaction of wave with a defect just after the excitation. On the bottom figure, the wave propagated for 100 microseconds and was scattered by another defect in the investigated sample. The example on the right shows an aircraft panel with a lot of rivets and a piezoelectric sensor at the center. The result of measurement with the laser vibrometer is shown at the bottom. We can see that the wave propagating in the structure is converting at various locations. These locations are related to the position of the rivets in this aircraft panel. Another example here is shown for a Cfrp panel. This is a sandwich structure with a aluminium core and simulated delamination as shown here, and the result is at the bottom. We can see wave scattering at this defect and clear visualization of the position of the damage. The example on the right shows us the Cfrp panel with a stiffener. The stiffener was locally debonded to investigate how the wave propagates in such locally debonded structure. The result at the bottom shows that the debonded region acts as a tunnel for the wave and allows wave to pass through to the other side. We also see a rough estimation of the size of this debond where the wave was traveling through this region. The remaining part of the stiffener is reflecting back the wave and stopping its propagation. Coming to signal processing approaches, if we consider sensor networks, the two most popular techniques is ellipsis-based and hyperbola-based. The ellipsis-based method analyzes the time of flight from the actuator to an arbitrary point and to the sensor, while the hyperbola-based method uses actuator and two sensors and analyzes the time difference of arrival at 1 and second sensor. The results of such methods are shown here that indicate the locations of the defects investigated object. The problem of placing of the sensors is very crucial in our studies. So there are various approaches how to place properly the sensors on a surface of the structure in order to obtain good damage assessment results. Here I would like to show one example how we employed a genetic algorithm in order to deploy sensors on investigated structures. The first academic example is a triangular plate, and the cost function is based on coverage, and the coverage is the coverage parameters are designed especially for the ellipsis-based method that was shown before. The optimal placement that was obtained by the algorithm is shown in this figure, and on the right we can see what is the coverage level of the whole area that was investigated. Next, we undertook a more challenging task of sensor placement for a Cfrp composite. So here we had the wave propagation that is dependent on the fiber orientation, and we also included a stiffener in this plate. There are some results of our studies. So we assumed 72 candidate locations for the sensors, and if we use all of them for localization, the result is shown on top left corner. But we assume that we would like to use less sensors, so we picked 8 as an arbitrary number, and at the bottom we randomly placed these 8 sensors and plotted the coverage. And now, looking at the results of the optimization, we can see that after 5,000 generations, the genetic algorithm give us such result. But using 10,000 generations, the result is already symmetric, and we have such trapezoidal shapes of the sensor placement on each side of the stiffener. And the coverage obtained with each placement is shown here in the table. So the optimal placement obtained with the genetic algorithm gives very nice result, far better than the random placement. The second method that I would like to present is the electromechanical impedance, where we investigate the electrical parameters as a function of frequency. These electrical parameters are measured at piezoelectric sensors that are bonded to the inspected structure. Here is a Cfrp plate instrumented with 4 sensors, and the damage that was introduced here was an impact damage. There were in total 4 impacts, 2 made at the same location, A and A prime. Next there was a B impact and C impact in such sequence. All of these impacts were made with 30 joule energy. Think of the data, we propose to use the principal component analysis, and we also propose 2 approaches. First one, called the classification approach, that we use all the measured data, meaning the reference data for the plate without damage, and later the damage data for the plate after the impacts. The PCA was performed for this data. Later the results were visualized in the new coordinate system defined by the first 2 principal components. In the second approach, we call this novelty detection. At the beginning we used only the reference data that was processed by the PCA, and after having the new coordinate system defined by the PC, we projected on this space the damage cases measured after the impacts. And here we try to differentiate if we can detect the damage. The result of the classification, so we can see that the sensors that are far away from the damage are clustered separately. So this is P1 and P4. The P3 cluster is over here, P2 is over here, and we have one more data point over here that is related to the last impact case. So here the damage to the plate was most severe. So we had 4 impacts, and this case showing largest differences. In the second approach, we assume that we have only reference data for the sensor number 4, And we checked if we are able to see any influence of the damage severity here. Our reference was the result with the RMSD index that was fluctuating for all the cases and didn't indicate it even for
Okay, I got the feeling that now we are a little bit over time. Therefore, may I suggest to my co-host to stop the video, and we can access the video at any later time when we can. So our next speaker is Sergey Makarov. So from Sergey Makarov from ITMO University Russian Federation, and he will speak about Halite Perovskites for applications in nanophotonics. Okay, Sergey, so please share screen with us and check the sound and the video.
Yeah, thanks, Mr. Chairman. Can you see my screen?
Yes, can you make it full screen, please? Yes, we can hear you and we can see you.
Yeah, dear colleagues, it's my great pleasure to present my presentation here on Halite Perovskites for applications in nanophotonics. And what is the nanophotonics? So basically, nanophotonics can be divided on two main parts. One is related to metallic nanostructures and dealing with plasmons, and so-called older-electric nanophotonics is dealing with dielectric and semiconductor nanostructures, nanoparticles, which support not plasmons, but resonances in these nanostructures. And there are some basic designs in this field, like nanocavities, nanoresonators, complicated nanoantennas, and metasurfaces. And the main advantages of the dielectric and semiconductor nanophotonics as compared with plasmonics is that it deals with light-emitting materials. And there are plenty of fascinating applications like lasers, LEDs, and so on, which are included in these fields. And the main challenge here is to develop materials with great light emitter and optoelectronic properties. One of these materials is the family of Halite Perovskites. So perovskites, the class of materials which were found firstly in Russian Empire by German scientist Gustav Rose. And then in 20th century, this type of structure was described by Victor Goldschmidt. And there are a lot of materials of these types were discovered, but Halite perovskites in the class of materials where we have halides in the very end of this formula, IBX3, and there can be all inorganic Halite perovskites and organic inorganic Halite perovskites, which were recently applied successfully not only for solar cells, but also for perovskite LEDs and perovskite lasers as well. So what are the basic properties of Halite perovskites? First of all, it's a direct band gap material with tunable band gap by replacement of halides in the very end of the formula. And their transition, interband transition, is stronger even than for gallium arsenide. Also, this is mid-refractive index material with refractive index line between 2 and 3, and which is higher than for polymers. And we can provide a good contrast for these nanostructures made of these materials. So these materials have high absorption, even better than in gallium arsenide, but we use normally epitaxial-free methods, so it's much cheaper. And also light emitting properties of these materials are very nice as well, because this is so-called defect-tolerant material, and it's very robust to formation of defects in the structure, allowing to preserve light emitting properties. And for nanophotonics, why we are interested in this material? Because it's low cost, it provides good optical contrast, it has tunable excitons at room temperature over whole visible range, and it has high quantum yield, and also high optical gain, which is important for lasing applications. So I will start my talk from so I will focus on the nanostructures and nanoparticles with sizes more than 100 nanometers. So it means that we should forget about quantum confinement effect. We should think about only optical resonances. And what type of methods can be applied for structuring of perovskites, for creation of nanoparticles? It can be laser printing method. It can be directly synthesized nanoparticles. We can apply nanolithography to create metasurfaces and nanostructures made of perovskites. And of course, it can be made of different compositions, provide different colors of emission for materials. And in the very beginning, I will start from the very background thing, very basic thing, like theory by Gustav Mie. It was developed in the very beginning of 20th century that light irradiating nanoparticle can excite two types of modes, electrical type modes, magnetic type of modes, which provide different various optical resonances. And you see here some examples of perovskite nanostructures. It can be spherical, cubical, or like discs, and made of different composition, providing different colors. We can calculate further scattering efficiencies from such nanoparticles, sub-wavelength nanoparticles. And you see here the maps where we have different positions of resonances for different wavelengths and for different sizes of nanoparticles, perovskite nanoparticles. One of the effects in all the electrical nanophotonics, if we can then combine electric and magnetic resonances at one frequency, and then look what is going on with the incident light. So, and there is so-called Kerker condition where we can suppress reflection from the layer of such nanoparticles made of perovskites. So we provide firstly numerical calculations for the array of such nanoparticles made of perovskites, and we observe that there is some minimum in integral reflectance for such metasurfaces, and then we fabricated metasurfaces made of this material. And you see here that in reflection we have suppression of reflection from 30% down to even up to 5%. And this is because of improved transmittance of this array. And still, we have good photoluminescence. We have even enhanced photoluminescence from this square, meaning that we, by Mie resonances, we not only manipulate by light, but direction of scattering of light, but also we provide some enhancement of photoexcitation and emission of this layer. Also, fundamentally, it's interesting to see what is going on when we couple excitonic state with Mie resonances. And according to our measurements and calculations, we observe that coupling of Mie resonance and exciton always results in some minimum in spectra, in scattering spectra. And this minimum is due to Fano resonance when we overlap narrow exciton and quite relatively broadband Mie resonances. We always have Fano-shaped resonances in this case. But the question is, can we tune such kind of resonances, and how strongly can we tune it? And according to, so perovskites is a very interesting material because we can provide a very simple reaction like anion exchange reaction, even for thin film. So you see here, if we take a bromide perovskite, then put some H chloride acid just nearby, and then wait for some time, we can provide some doping from vapors of this acid, and we can completely replace bromide by chloride. And it results in dramatic change of band gap. So we see here ellipsometry data that refractive index changes quite a lot during the doping just after several minutes. And we see that excitonic properties are still preserving, which is very important for excitonic applications. And the same story is, can be applied for array of nanoparticles made of Halite Perovskites. And you see here some experimental results, how we tune this Fano deep resonance over half of our visible range, and which is confirmed by our theoretical calculations. And it's interestingly that is it reversible or not? Of course, yes. Yeah, because if we take the nanoparticles made of bromide perovskites and put in acid of H chlorine and wait for some time, we can shift our extinction spectra over more than 100 nanometers to the UV range. And then we can put exactly the same nanoparticles in H bromide acid, and then we'll take the same nanoparticle as we had in the very beginning. So, and we can do it due to complete doping or partial doping, and we can apply many cycles in this chemical reaction to provide multi-cycle tuning of our nanoparticles, nanoantennas. So also, funnel resonance can be tuned in ultra-fast manner. So as you see in this application, we demonstrated ultra-fast tuning just in less than 1 picosecond at some wavelengths. We can modify the properties of these funnel resonances quite dramatically. So, and then I switch to my presentation, how we can apply this resonant nanophotonics for nanolasers, because nanolasers is one of the most brightest application in nanophotonics. So we employ the material like cesium lead bromide, which provides us very nicely shaped nanoparticles, which are submicron nanoparticles. And we grow them on sapphire substrate, which is important because we have to provide as high as possible quality of the crystal. And the question is what the quality factor of nanocavities for lasing, because previously perovskites were used for lasing as in form of microplates or nanowire, but with microscale lengths. But if we use completely sub-wavelength nanoparticles, what Q factors can we expect for these designs? And we provided calculations for different shapes of nanoparticles, and we observed that for sub-wavelength particles less than one wavelengths, we can observe the Q factors is between just maybe 10 and 100. So we should work somewhere in this range. And we fabricated such nanoparticles and then tested their lasing properties. We observed a threshold-like appearance of narrow peaks in the visible range, and we observe also mirror resonances and scattering. Also, after characterization of different nanoparticles, we observed the different levels of threshold for each nanoparticles. And we observed the smallest nanoparticle supporting lasing in visible range is a nanoparticle of the size closing to λ/2. And this corresponds to magnetic octopole resonance. This is the results of our decomposition, mode decompositions. And interestingly, that this is world record among nanolasers, non-plasmonic nanolasers working at room temperature in visible range, as you can see here. So this is because of very high gain of perovskites. And once we can create a perovskite lasers, nanolasers, microlasers, it's tempting to integrate them with nano waveguides. So what is the best material for waveguiding in the visible range? Of course, it's not silicon, because silicon has very high losses in visible range. So according to the best of our knowledge, gallium phosphide is one of the best material for this spectral range for green light. You see here the dispersion for this material, and it has very high refractive index and very low losses, just above the 500 nanometer. So we fabricated gallium phosphide nanowires, and then
Makarov, 1 minute left.
Yes, thanks. And fabricated such micro lasers with integrated nanowires. As you can see here, some examples of integrated nanowires in micro lasers. And then we integrate them even with other perovskite nanoparticles and other waveguides. And these lasers also can be tunable due to this anion exchange reaction. And you see here that in vapor of acids, we can just reversibly tune the color of such lasers, which is quite unique among the semiconductors. And the final stage of my talk, I would show just how we can scale up the technology of fabrication of micro lasers made of perovskites. So for scaling up, we applied the laser ablation technique, because perovskites are very robust, defect-tolerant material and allow to create micro lasers with a high quality over centimeter scale. So we see here the billions of lasers fabricated just in 10 minutes. So, and it can be applied for different colors for different perovskites. And we see that by laser ablation, we can fabricate even nanowires made of these materials. And to sum up, so I would like to stress here that all the electric nanophotonics dealing with mirror resonances, Fabry-Pero resonances, and various resonances which we have in semiconductor nanostructures is perfectly can be applied for perovskite materials for tuning, for ultra-fast switching, and for record small nanolasers, which can be integrated successfully with nano waveguides and then upscaled in the centimeter scales. So thank you for your very kind attention.
Okay, thank you, Dr. Makarov. Nice talk. So our next speaker is Dr. Dvaipayan Chakrabarty from University of Birmingham, UK. His talk is about colloidal photonic crystals, Mind the Gap. I have the feeling that Dr. Chakrabarty is live, but he expresses the desire to play the video. So therefore, we can play the video. Thank you. Now, it seems that we have an issue with the sound, but let's try our best.
Sorry, it's not the sharing issue. It's the issue come with the video. The sound doesn't come out.
We don't have a sound.
Yes.
Okay, that's a new situation. I don't know. So, well, let's see if Dr. Chakrabarty can listen to us. Dr. Chakrabarty, are you live? Would you be brave enough to continue live, or basically it's not possible?
Hello, can you hear me?
Yes, we can hear you. We are having a problem with your video that has no sound for some reason that we don't understand. So I was wondering if you are brave enough to to come live and sort of make your presentation.
Okay, I'll give it a go. The internet permitting. So let me try to share the screen.
Okay, if you are lucky, we might get everything running. Okay, we can see your screen.
Okay, give me 1 second. Okay, thanks for the invitation. Today I'm going to talk about programming self-assembly of colloidal photonic crystals. Photonic crystals are composite media that provide a platform for controlling the flow of electromagnetic waves, typically because of the existence of a photonic band gap, which prohibits electromagnetic waves corresponding to the gap frequencies to propagate through the crystals. If these crystals are built from colloidal particles in the size range of hundreds of nanometers, we can have a platform for visible light management. Self-assembly of designer colloidal particles appeals as a low-cost scalable fabrication route. However, the most sought-after colloidal photonic crystals have rather open structures comprising low-coordinated colloidal particles, making them challenging targets for programmed self-assembly. Additionally, stacking faults in these self-assembled colloidal open crystals tend to compromise their photonic band gaps. Our focus here is on tetrastack and diamond crystals, the cubic polymorph of which were known to support a complete photonic band gap for a relatively low refractive index contrast. Let us take a close look into this series of cubic crystals starting from the face-centered cubic on the left. The packing fraction gradually drops with a decrease in the mean coordination number. Going by the Maxwellian counting rule, when the mean coordination number falls below twice the dimensionality of the lattice becomes mechanically unstable for isotropic colloidal particles. The so-called Maxwellian lattices are in balance building blocks. The target structure is not only thermodynamically favored, but also kinetically accessible. The Granick group provided a major breakthrough in self-assembling colloidal open crystals about 10 years back. A Kagome lattice was self-assembled from tri-block patchy particles in a quasi-two-dimensional system. Here, the designer colloidal building blocks have equal size attractive patches at the poles across a charged middle band. Upon screening the electrostatic repulsion between the particles by throwing salt into the medium, the self-assembly was observed. This seminal work provided
Well, I guess we are having some issues with Dr. Chakrabarty, right? So, well, maybe after all we can try to play perhaps the last 3-4 minutes of his video, and we can wrap up sort of the time slot. So that's an idea. So Dr. Chakrabarty, can you hear me? Or we lost you?
Or I can play his video, to prefer that way.
Well, yeah, Dr. Chan, perhaps we can play perhaps the last 2-3 minutes of Chakrabarty's video without the sound, because we cannot fix it, and we move them to the next speaker, right? Thank you.
Hello. Can you hear me?
Okay, now we can hear you, Dr. Chakrabarty. Well, so we suggest you move on to perhaps the last 2 minutes of your presentation, and then we wrap up this part, since we had all these technical issues, right?
I'm not sure, like, why you lost me.
I have no idea. It is Murphy's law. If something may go wrong, it will. So again, yeah, can you go back perhaps and connect to the last part, considering all?
Can you see my screen?
Yes, now we can see it. Yes. Right. Yeah, the basic idea is, if you connect kind of this part to what are the most important ideas at the end, and we wrap up the session, right?
Do you want me to start again?
No, I want you to pick up from where you stopped and then move forward a little bit faster because of kind of time limitations, right? So that we do not.
I think I was here when you lost me. Let me give it a go from here. So, for example, Romano and Sortino captured the self-assembly of the Kagame lattice from tri-block patchy particles at low temperatures and pressures. And predicted the formation of the closed-back hexagonal lattice at higher pressures. The state-of-the-art experimental fabrication has control over the patch width. In a subsequent experimental study, the Granick group induced staged assembly in 3D by changing the ionic strength of the medium in steps. However, the first stage produced a distribution of clusters leading to the self-assembly of an amorphous structures in the second stage. For such a two-stage assembly to yield a colloidal crystal, a major challenge is to ensure that the first stage produced uniform clusters rather than distribution for them to act effectively as a monodisperse secondary building blocks in the second stage. These colloidal clusters, mimicking the symmetry of small molecules, are referred to as colloidal molecules in the literature. I now illustrate how we have addressed these challenges in the context of self-assembly of colloidal photonic crystals. Our hypothesis is that a hierarchy of interaction strengths realized with tri-block patchy particles can encode hierarchical self-assembly. Here, the patches on the opposite poles are labeled A and B. An A patch makes strong bonds with another A patch. The BB bond is weakest. A bond between patches A and B is not ruled out here, but is of intermediate strength. We optimize the patch width and the range over which these patches interact along with the inverse Debye length by finding the global minima on the potential energy landscapes. These structures clearly show structural hierarchy via tetrahedra and octahedra for two sets of parameters which both encode a hierarchy of interaction strengths. We find that a wider patch width for the stronger patch and a longer range for patch-patch interactions favor the formation of octahedra over tetrahedra as expected. The interactions between the weaker patches bring these colloidal molecules together. Let me now specifically discuss the self-assembly of tetrastack crystal, which can be viewed as cornered shared tetrahedra here. In an ideal tetrastack crystal, these tetrahedra are equivalent, but I have color-coded them to distinguish between two sets of tetrahedra. By focusing on this tetrahedron, what I would like us to recognize is that one set of tetrahedra can emerge from the assembly of the other set of tetrahedra. Our designer tri-block patchy particles then have equal size patches on the poles, but a hierarchy of interaction strengths to encode stage self-assembly pathways. The crystal structure prediction confirms that such a designer building blocks can indeed stabilize both the cubic and the hexagonal polymorphs, which are of equal energies on the crystal energy landscape. A series of Monte Carlo simulations with 500 particles under periodic boundary conditions show that a tetrastack crystal can indeed be self-assembled from our designer tri-block patchy particles. If we monitor the number of tetrahedra formed in the system as the system is gradually cooled, we find that the tetrahedra are eventually exclusively formed by the interactions between the stronger patches. A rapid growth of the number of tetrahedra signals crystallization driven by the interactions between the weaker patches. Note that the crystal structures are stable even in the absence of hierarchy of interaction strengths. However, our Monte Carlo simulation studies yield an amorphous structures, though with comparable number of tetrahedra. The pair distribution functions for the sets of tetrahedra show that the no long-range order emerges in the absence of hierarchy of interaction strengths, in which case we talk about AA tri-block patchy particles. A pertinent question is how hierarchical self-assembly pathways promote crystallization in this case. The answer lies in the ring statistics. As shown here, the perfect crystal has 6 and 8-membered rings. The ring statistics show that the two-stage self-assembly via tetrahedra suppresses the formation of 5 and 7-membered rings, which when present prohibit the emergence of long-range order. I'm now going to extend this design approach to reverse engineer the so-called rod-connected diamond structure, which is known to be the champion photonic crystal because it supports the largest photonic band gap. Here, rods connect the nearest neighbor sides of the diamond lattice. A retrosynthetic approach on the colloidal scale for following the two-stage disassembly scheme takes us to tri-block patchy particles, but now one with an elongated core. Because of the tetrahedral voids, we refer to this structure as segmented rod-connected diamond. Such tri-block patchy particles are now indeed synthetically available, as shown here. To cut a long story short, the two-stage self-assembly does work here as summarized on this slide. The important point to note, it works for a range of aspect ratios. In the limit of L star equal to 0, we have a tetrastack crystal. However, the self-assembly yields a mixed phase of both cubic and hexagonal components. For the segmented rod-connected diamond structure, we find that both the cubic and the hexagonal polymorphs support a complete photonic band gap, and the band gaps spectrally overlap. We calculated the photonic band structures for randomly stacked structures. On average, we find that the photonic band gap survives, and it can be maximized with an optimal choice of L star values. Remarkably, the photonic band gap of this segmented rod-connected diamond structure is thus found to be robust to stacking faults. Once we understood the physical mechanism by which the hierarchical self-assembly that prevents the formation of AB bonds.
Hey, Dr.
We ensure that there are no thermodynamic.
Last minute, please.
Yeah. We ensure that there are no thermodynamic driving forces for the formation AB bonds. Such specificity in the patch-patch interactions could be realized using DNA-mediated interactions in synthetic colloids. Seeing is believing. This route also yields the crystal. The formation of 6 and 8-membered rings signals crystallization, which interestingly in this case occurs in 2 steps with a growth of tetrahedral ordering prior to nucleation. Let me
Okay, Dr. Chakrabarty, let's close it here then. Thank you very much for coming in such a brief notice, kind of to help us in this matter. So let's move on then to the next speaker. That is Dr. Arvind Kumar from CSIR Research Institute, India. He will talk about ionic liquids-based colloidal solutions as nanoreactors for advanced materials. Arvind, are you present live? I don't see his name, so I guess let's put the video live.
My name is Dr. Arvind Kumar from CSIR Central Salt and Marine Chemicals Research Institute, Bhavnagar, India. So before I start, I must acknowledge Organizing Committee of Advances in Functional Materials Conference, my research scholars, particularly Mr. Sanjay Mehra, Krishna Damarla, Veera Babu, and other scholars working in my lab. I should also acknowledge Director, CSMCRI, and my colleagues, collaborators, and project sponsors. So topic of today's talk is ionic liquid-based colloidal formulations as nanoreactors for advanced materials. So thanks again for inviting me for this talk. So structure of the talk will be like, we shall be describing conventional methods of advanced material synthesis, such as metal organic framework synthesis, and then why microemulsions for advanced material synthesis are more important. And then we will be discussing ionic liquid-based colloidal systems. And then I will be giving an example of an ionic liquid-based colloidal solution, which is acting as nanoreactors for synthesis of metal organic frameworks. And finally, I will be concluding my talk with future prospects and give some conclusive remarks. So the conventional methods of nanomaterial synthesis, if we see, there are different methods like diffusion, solvothermal, microwave, mechanochemical, and electrochemical techniques. These are generally used to synthesize metal organic frameworks. These methods, although they have certain advantages like materials with a good control over size and shape and crystallinity are produced by using these methods, but these methods have certain disadvantages also. These methods are very energy consuming and require harsh conditions of temperature and pressure for the synthesis. And most of the synthetic procedures for MOF preparation involve liquid phase reactions and are not suitable in common organic solvents. So it is difficult to synthesize different kinds of MOFs with a single approach using conventional methods, and recyclability is also an issue with these methods. So herein we are trying surfactants assisted material synthesis, and these methods can overcome all these limitations. So use of microemulsions or micellar systems as nanoreactors for material synthesis will be demonstrated in this talk. If we look at the nature of surfactants, so ionic liquids can also be designed as surfactants because they are tunable in nature, and we can make surface active ionic liquids just by incorporating amphiphilicity in constituent ions of the ionic liquids. So they can be cationic surfactants with hydrophobic tail is attached with cation. Then they can be anionic surface active ionic liquids. One can make biamphiphilic ionic liquids, double chain ionic liquid surfactants, stimuli responsive, bio-based, magnetic, or metal-based. So different kind of surface active ionic liquid can be synthesized depending upon the choice of cations and anions. Herein we have produced a single chain cationic surfactant by incorporating hydrophobic group in imidazolide group, and then anionic surface active ionic liquids have been synthesized by incorporating long chain with the anionic head group, and then similarly we have made biamphiphilic kind of ionic liquids by incorporating chain both in cation as well as in anion. And several other surface active ionic liquids like double chain surface active ionic liquids have been constructed. And then we also introduced stimuli responsive ionic liquids by taking cationic part as well as delocalized pi electrons in anionic part. So such kind of ionic liquid surfactants have been produced by us. And as far as solvents are concerned, ionic liquids can also be used as a media which can support the self-assembly of surfactants. So here low viscosity ionic liquids can be used as solvent medium wherein ionic liquids can self-assemble and make colloidal solutions. One can see these different structures. One can construct colloidal solutions of ionic liquid as micellar solutions. One can construct vesicular solutions. And if in these kind of colloidal solutions, if oil phase is added, microemulsion droplets can be produced. So we are interested in producing these ionic liquid based colloidal solutions and to use them in the synthesis of nanomaterials, particularly metal organic frameworks. So if you look at different categories of ionic liquid based colloidal systems, they can be two component systems where ionic liquid is surfactant and other medium is either water or organic solvents. then one can have a more robust system where ionic liquid is surfactant and ionic liquid as a polar or non-polar medium. So these micellar structures can be formed, and one can make colloidal solutions of 3-component systems wherein ionic liquids can act as surfactant, ionic liquid can act as polar medium, or ionic liquid as polar non-polar medium. So using all the 3 components, one can make very robust ionic liquid based colloidal solutions or microemulsions, which can be used as a nanoreactors for the synthesis of different kinds of nanomaterials. Herein, we will be providing one example wherein we constructed microemulsions consisting of choline AOT based ionic liquid as a surfactant, ethylene glycol or hydroxyethyl formate as a polar medium, and a vegetable oil L-limonene as a oil phase. So initially we determined the aggregation behavior of choline AOT in ethylene glycol as well as in hydroxyl ethyl formate and in oil phase. And if you can see the isothermal titration plots, so it gives clear signatures where choline AOT is aggregated in the medium, and in non-polar medium, or one can say in limonene, so this curve is different, but there is a clear aggregation of choline AOT in non-polar medium also. And from the thermodynamic properties derived, we can see that delta G of aggregation is negative in all the cases. So there is a very good feasibility of aggregation of choline AOT in ethylene glycol as well as ethyl ammonium formate and in limonene. So by finding that these can be aggregated in ionic liquid medium or ethylene glycol medium, we constructed the microemulsions of these components. Here we can see the ternary phase diagrams of choline AOT in ethylene glycol with limonene as a oil phase. And the right side ternary phase diagram is we have replaced ethylene glycol with hydroxyethyl ammonium formate as a polar phase. And in both the systems, we found that there is a very large monophasic region which is formed without using a co-surfactant. So very robust microemulsions of ionic liquids in ionic liquid systems were constructed, and the droplet size in the microemulsions in case of ethylene glycol, it ranges from 10 nanometer to 40 nanometer hydrodynamic radii, and in case of hydroxyl ethyl ammonium formate, the droplets were little smaller, and the size of the droplet increased with the increase in R value in both the cases. So there was a clear swelling behavior in the microemulsion drops, and these droplets were used as a reactors, as a nano reactors for MOF material synthesis in a cyclic manner. So we took the precursors, metal as well as ligands, and mixed them in microemulsions, and we could synthesize the material at room temperature within a very short period of 6 hours, and these materials could be easily extracted just by bursting the microemulsions. And then the system was regenerated and again utilized for the synthesis of next batch of nanomaterials. And for our wonder, when we replaced ethylene glycol in the medium with an ionic liquid, we could synthesize different kind of metal organic framework with a single microemulsion systems. We synthesized aluminium-based MOF, zirconium-based MOF, zinc-based. So all kinds of MOFs could be synthesized in an ionic liquid-based microemulsion system. These microemulsion droplets were synthesized, were used to synthesize different types of metal organic frameworks. Initially, we synthesized copper-based MOF, HCUST, using copper nitrate and benzene tricarboxylic acid precursors. They were mixed in microemulsion systems, and at room temperature, we got MOF with spherical morphology, which were characterized for surface area and CO2 adsorption properties. Likewise, we synthesized zirconium-based MOF using zirconium chloride and 2-amino terephthalic acid. These were again characterized or synthesized in microemulsions and characterized for surface area and gas adsorption desorption properties. Again, we synthesized aluminum-based metal organic framework using aluminum nitrate and 2-amino terephthalic acid as precursors. These were mixed in microemulsion systems, and at room temperature, we synthesized spherical aluminum-based MOF, which were characterized for surface area and gas adsorption desorption properties. Further, we could also synthesize zinc-based GIF8 metal organic framework using zinc nitrate precursors. They were mixed in microemulsion systems, and again at room temperature, a uniform morphology spherical MOFs with nano size were synthesized, which were characterized for surface area and carbon dioxide adsorption studies. All these MOFs were characterized for their crystallinity and their other physical properties. So these MOFs were found to be very good crystalline in nature, and surface area of the synthesized MOFs was moderate as compared to the MOFs synthesized by other conventional methods. CO2 uptake was also moderate for the materials synthesized using these methods. These material or metal organic frameworks were used to prepare thin nano composite nanofiltration membranes utilizing piperazine, tremisol chloride, and metal organic frameworks synthesized using microemulsion droplets. We formulated different nanofiltration membranes which were tested for the separation of mixture of salts. So we took mixture of magnesium sulfate, sodium sulfate, and sodium chloride, and using the prepared thin nanocomposite filtration membranes, we can see that all the salts were easily separated using these membranes. Therefore, we can say that these kind of microemulsions were utilized as a universal nanoreactors for the synthesis of materials, and the future prospects of these kind of microemulsions is, so microemulsion based nanomaterials synthesized so far have certain limitations of surface area, porosity, and recyclability. But herein we anticipate that novel ionic liquid based nanoreactors can be constructed from economically or biological resources with a judicious choice of cations and anions that is suitable for synthesis of advanced energy materials with better physicochemical properties. And to sum up, we can summarize the results that ionic liquid can be developed and used as novel surfactants for diverse applications. They can be developed as surfactants, and we can construct microemulsion systems which are consisting of ionic liquid surfactant and ionic liquid medium, and we can use them as cyclic reactors for synthesis of variety of metal organic frameworks based on different type of precursors. We can synthesize this with precise control of size and morphology at room temperature and demonstrate a universal approach for metal organic frameworks preparation. So again, I thank my research scholars who dedicatedly worked for this, project, and thank you very much. Thank you, all of you.
Okay, wonderful. So we have come now to our very last speaker. Our very last speaker is Célia Souza from Porto University in Portugal. And the title of her presentation is Vortex Nanostructures, from Micromagnetic Simulations to Cancer Cells Internalization for Magnetomechanical Induced Damage Applications. So Célia has expressed a desire to have her video played. Therefore, I will ask my colleague, co-host, Dr. Chichian, to play Célia's video, please.
Hi everyone, my name is Célia Souza. I'm from Porto University in Portugal, and I'm going to present our work on vortex nanodiscs and also magnetic nanowires from micromagnetic simulations to cancer cells internalizations for applications in magnetochemical cell death. I will start with a brief motivation, then I will show you our main results in micromagnetic simulations. Then I will show you the fabrication route to obtain these nanodots, their magnetic properties, and the biomedical applications. I will show you also our recent results regarding the synthesis and characterization of high aspect ratio magnetic nanowires for biomedical applications. So, beyond the recent advantages in the conventional therapies of cancer, namely hormonal and targeted therapies, the recent advances in nanotechnology showed that several types of nanoparticles can be a good alternative for cancer treatment, since we can tune the size and the shape of the nanoparticles, the material and the surface functionalization can be changed depending on the specific type of cancer that we want to treat. In particular, nanowires and the nanodiscs showed several advantages compared with the spherical counterpart, namely regarding the increased turbulent flow, the increased contrast with the cells, the increased contact with the cells, as well as the reduction of organ accumulation depending on their shape, size, and also the surface charge. So, recently, magnetic nanodiscs in a vortex state show the ability to perform cancer cell destruction by a mechanical movement under low magnetic fields and low frequencies. Nanodiscs obtained by lithography techniques defined in a micro and nanoscale that possess a spin vortex ground state usually presents a high magnetic moment when compared with the superparamagnetic nanoparticles, and also present zero magnetization in remanence, which reduces the long-range magnetostatic forces that leads to the particle agglomeration, which is one of the most disadvantages of biomedical applications of these nanoparticles. Also compared with magnetic fluidic hyperthermia, vortex nanodiscs can work at low frequencies, low magnetic fields, and low concentrations of particles. Ideally, only one disc per cell is enough to perform the cell death. Before the sample fabrication, we performed micromagnetic simulations to define the experimental conditions to obtain the nanodiscs in a vortex state. MUMAX-3 was used to simulate iron nanodiscs with the 50 nanometers of thickness, exactly with the shape and the dimensions of the experimental samples for both single nanodiscs and array of nanodiscs. Using the simulations of nanodot arrays, we studied both the influence of interdot distance and several aspect ratios varying the values of diameter and the thickness of the iron layer in the nanodisc. The nucleation and the annihilation fields increases when we increase the distance between the nanodots, or the separation between the nanodots, up to 2 times of the radio of the disk. A stabilization of the magnetic susceptibility value is also observed for the same value of interdot distance. So, For an interdot distance higher than 2 times the radius of the nanodisk, no interactions between the nanostructures influences the sample behavior independently on the dot size. The thickness and the diameter of the disk are key parameters to define the dimensions to achieve the vortex state. Thus, the vortex characteristic fields, annihilation and nucleation fields are plotted with respect to the aspect ratio of the nanodisks, the diameter divided by the thickness in both axis and I direction. As the aspect ratio increases, a nonlinear decrease is observed in both nucleation and annihilation fields, in agreement with the already reported for vortex behavior. This behavior can be explained due to the competition between the demagnetization energy and the exchange energy. However, in the case of nucleation fields for low aspect ratio, lower than 7, in both directions, they appear to not follow the same trend as the others. This is maybe associated to the lower limit of the behavior, when the assumption of thin disks falls short and the remnant state trends to the single domain. Taking into account the results obtained in the micromagnetic simulations, we prepared by interference laser lithography templates with around 500 nanometers in diameter, and as mentioned before, for both directions, X and I direction, we have a slight difference diameter, as we can see here, associated to the method used to prepare these nanostructures. Then we grow a multi-layer film on the patterned substrate, first with deposited sacrificial layer of aluminum that will be then etched to release the discs in a solution, and then we grow gold nanodiscs by evaporation, where the gold layers are protective layers and the 50 nanometers thick iron layer is the active magnetic layer. Mach hysteresis loop measured in the prepared samples after the liftoff process clearly show the vortex state in iron nanodiscs with around 500 nanometers in diameter and 50 nanometers thick. Zero remnants is observed, and the annihilation and the nucleation fields were determined and are in a good agreement with the magnetic simulations in the X direction. Finally, the nanodiscs were removed from the substrate by an etching process of the aluminum layer, and the nanodiscs were dispersed in a buffer solution and incubated with the human leukemia monocytes to evaluate the internalization of the nanodiscs by the cells and their biocompatibility. So, as we can see here, we achieved a good viability with less than 10% of cell death for each concentrations up to 120 nanodiscs per cell, and we also achieve a particle uptake, as we can see here, with a saturation reached between 80 and 120 discs per cell. So we can conclude that our nanodiscs are biocompatible and were also internalized by the cells. We also prepared iron nanowires by using a template-assisted method. First, we prepared anodic aluminum oxide templates by a two-step anodization process, and then we filled the pores of the templates by an electrodeposition method. We use a co-deposition method to deposit iron and copper layers. In this case, copper are only a dead layer to increase the number of layers of iron and then increase the amount of nanowires per sample. The electrodeposition behavior was monitored for each layer of both materials. And as we can see here in these scanning electron microscopy images, we are able to deposit iron copper multi-layered nanowires, and we are also able to change the length of the nanowires depending on the electrodeposition time. So we performed the structural characterization of these nanostructures, and we obtained for the iron nanowires a BCC structure with a preferential direction along the 110 direction. Regarding the magnetic behavior, we can see that by increasing the copper segment thickness between the iron nanodiscs, one evolves from samples with a marked easy axis, as we can see here, dominated by a shape anisotropy, to an almost isotropic behavior when we increase the separation between the iron layers. So, to evaluate the interaction between these nanowires, we also performed the fork analysis, and as we can see here, for a lower separation between the iron nanodiscs, we see behavior that is dominated by the dipolar interactions between the iron nanodiscs, and the iron nanodiscs have a behavior like a continuous nanowires without the copper layers. When we increase the copper layer, we see that the individual behavior of these iron nanodiscs. We also changed it, we also tuned the thickness of the iron nanowires from 20 nanometers, like a disc, up to 300 nanometers in length in the case where we have a high aspect ratio nanowires. And as we can see here, we can go from a low aspect ratio behavior of the particles with an isotropic behavior up to behavior of a high aspect ratio nanowire dominated by the shape anisotropy. To evaluate the possibility to use these nanowires for biomedical applications, we performed the dispersion of iron nanowires in a solution. First, we removed the alumina membrane, then we removed the copper layer by selective etching and obtaining a suspension of iron nanowires. These nanowires showed to have a biocompatible behavior with less than 15% of cell dead, and we are also able to uptake up to 120 nanowires per cell. So now we are working with the multifunctional nanostructure. So we are working, we put our magnetic nanostructures inside lipid shells that also have a drug inside. So the white part is the lipid shell and the black part are our magnetic nanostructures for application in controlled drug delivery and magnetomechanical cell death. So, as a conclusions, we performed a systematic study of the magnetic properties of iron nanodiscs and iron nanowires by using micromagnetic simulations. We also obtain thermally evaporated gold nanodiscs in a vortex state, and also iron nanowires with a controllable length and interwire distance were synthesized and characterized. Both nanostructures, nanodiscs and nanowires, showed a biocompatible behavior, and also both structures were successfully internalized in cancer cells that can be used for future magnetomechanical cell death assays. I have to acknowledge to a lot of people from different institutions in Porto University and University of Basque Country, and thank you very much for your attention and your time. Thank you very much.
Okay, thank you very much, Celia. Okay, so I guess so this is the moment for some concluding remarks. So may I say that it was wonderful to have all of you presenting these wonderful works, and at this juncture I want to thank all the speakers, session chairs, and volunteers for their help to successfully run this conference. So we hope to see all of you next year physically at UCLA. So with that said, I declare the closing of this session, and I believe that this is time for all of us. We can freely leave the meeting and wrap up the session. Thank you very much.
Thank you. Thanks for sharing.